Hi, my name is Ruby Feeney. I'm a Chem 6BL student, and today I'll be showing you how to make a pH indicator using red cabbage. So as we learned in methyl orange lab, a pH indicator changes colors based on the acidity or the basicity of the solution, and red cabbage contains a pigment molecule called anthocyanin, and this is a water-soluble molecule that gives a lot of vegetables their color as purple, blue, and red. And so similar to methyl orange, anthocyanin is a highly conjugated system with delocalized electrons, and it absorbs light in the visible region of the wavelength spectrum. So remember that molecules that are lower in energy absorb longer wavelengths. And in methyl orange, we saw that in acidic conditions, the protonation led to a longer conjugation system, which was lower energy and absorbed longer wavelengths. And today we are going to see the opposite is true. So this is what a neutral anthocyanin molecule looks like. And this is going to be observed as purple. And so in acidic conditions, at low pH, we're going to see that there's protonation that causes a shorter conjugation system. And so in this case, we will see shorter wavelengths of around 400 to 500 are absorbed, meaning that green light is being absorbed and red light is going to be observed. So at low pH, we are going to see red. And in basic conditions, we are going to see that there is now a negative, and this is now deprotonated. So this is going to have a longer conjugation system because of these delocalized electrons. And so in basic conditions, we see more conjugation due to the deprotonation, which means the molecule is now lower in energy and will absorb longer wavelengths, such as 600 to 700 nanometers, meaning that orange light is being absorbed and blue light will be observed. So to summarize, anthocyanins are purple in neutral conditions around 7 pH, and they are red in acidic conditions, which we will see that this is usually the most obvious when the pH is less than 4. And in basic conditions at high pH, they will be blue. So overall, more conjugation means lower energy and longer wavelengths being absorbed, and in our case, that will correlate to blue color. So today I'm going to make a pH indicator using red cabbage, and then I'm going to test the pH of different things I can find around my house. Okay, so what I'm using to do this experiment is a couple leaves from a red cabbage, some warm water, a measuring cup, a blender, a colander, something to pour your mixture into, so I have a big bowl, and then a bunch of clear glasses to test your different solutions in, and then whatever you feel like testing, I'm going to do baking soda, lemon juice, oat milk, and pickle juice. So I started off by boiling some water, and now that it is warm to the touch, I'm going to pour 4 cups into my blender. Now that my 4 cups are in, I'm going to take some leaves off of this red cabbage and try to fit as many as I can in there. Okay, so now that I have my red cabbage in my blender with warm water, I'm just going to blend it. Okay, so I just blended all of my cabbage water, and we see that I got a super pretty dark purple color, and now I am just going to strain that mixture using the only colander that I have in my house, which is very small, into another bowl. Okay, so now I'm going to transfer my strained purple cabbage juice into some clear glasses that I'm going to test different solutions in, and then I'm going to keep one of just the cabbage juice to compare to. Okay, so now I have laid out my 4 solutions of cabbage juice that I'm going to be testing against the different items that I have placed behind them. And then here is our control to compare to at the end. Okay, so this is the first one, this is lemon juice. So we can definitely see that it's getting lighter, it's getting more red, which makes sense because lemon juice is acidic, and we see that our solution is turning red. Okay, so next I'm going to add oat milk. So we see that it just got a little lighter, but it is still purple, meaning it is probably basic. And now I'm going to add pickle juice. So we can definitely see that it turned more red, but it is definitely not as red as the lemon juice, so it is probably less acidic than the lemon juice. And lastly, I'm going to add baking soda. Okay, so after stirring, you can definitely tell that that one got more blue. It's kind of hard to see on camera. Here it is next to the red lemon juice and the purple control. So we can say that our baking soda was a base because it turned blue. Okay, so I have organized all the results from most red on the left to most blue on the right, meaning lowest pH, most acidic, to highest pH, most basic. So we can see that lemon juice was the most red, meaning that it was the most acidic. And remember, this is because anthocyanins are protonated in acidic conditions, which shortens their conjugation system, meaning they are higher energy and absorb shorter wavelengths. So we end up seeing red. And the opposite is true in basic conditions, where deprotonation causes a longer conjugation system and longer wavelengths to be absorbed, so we observe blue. Okay, so I hope that this experiment helped refresh some of those concepts that we learned over the quarter about conjugation systems and how wavelength corresponds to the colors that we observe. Thank you for watching this video.